Welcome to the second part of 3A, where we'll be looking at the graphs of Cosec, Sec, and Cot. So this picture here gives you a sneak preview as to what these graphs look like, albeit all on the same axes. So before we get started into looking at what the graphs look like and how to construct them, let's look at a couple of properties that will be used when we're drawing these reciprocal functions. And the reason we're doing that is because your Cosec, Sec, and Cot, they're all related to the graphs that we should know already, which are sine, cos, and tan. So the sine, cos, and tan graphs, we pretty much know they're quite easy to draw. And the reason why they're related is because, of course, Cosec, Sec, and Cot are simply reciprocals of those other graphs respectively. So we're going to use some properties of reciprocals that will help us in sketching the graphs of Cosec, Sec, and Cot. Right, so let's go through them one by one. So if you have any original function and you take the reciprocal of it, there will be some features that will always be true. So here's the first one. If you have an original function and then you go to the reciprocal will have vertical asymptotes when the original graph had x-intercepts. So anytime the original graph has an x-intercept, a vertical asymptote will appear on the reciprocal graph. The vice versa is also true. When there are vertical asymptotes on the original graph, your reciprocal graph will have x-intercepts. So basically, x-intercepts and vertical asymptotes keep swapping between each other when you go from an original to a reciprocal. On a similar note, if you have a local minimum or a local maximum on the original graph, then the reciprocal will have a local max or local min. So basically, minimums swap over to maximums and vice versa. So a local maximum on an original graph will swap over to a local minimum on the reciprocal graph, and a local minimum on the original graph swaps over to a local maximum on the reciprocal graph. And finally, you need to be aware that signs are preserved. So what that means is if you have positive y values on the original graph, well, on the reciprocal graph they remain positive, and the same thing happens for negatives as well. Excellent. So keeping this in mind, we're now going to draw the graph of Cosec using the graph of sine as a template. So this is what we are going to do. You can see the graph of y equals sine x over here. I've drawn it over a domain of negative pi to x to 2 pi. So that's the domain I've drawn. I've drawn this sine graph over, and that's just for convenience, really. From 0 to 2 pi is really the part we're going to be looking at, but having something at negative pi is also good just to keep an eye on things. Right, so that's just y equals sine x. We're not going to do anything with that original graph there. What we are going to do is we're going to look at the bottom part over here. So you can almost, it's very faint, you can see it very faintly over there, but you can actually see the graph of sine x sort of in the background of that graph over there. Right, so let's do the first thing, and the first thing you should always aim to do is to draw the asymptotes. So the asymptotes of this graph are going to be basically at where the x-intercepts of sine are. So you can see that the graph of y equals sine x has an x-intercept at x equals 0, at x equals pi, at x equals 2 pi, and finally we have it at x equals negative pi as well. There we go. So there's our asymptotes. Now, as is always the case with asymptotes, it's always a good point to label the equations of these asymptotes. So let's do it just below the graph. So we have x equals 2 pi. Here we have x equals pi. Here we have x equals 0. And finally we have x equals negative pi. All right, so now let's look at what else we know. Well, let's look at the region between 0 and pi. So between 0 and pi, we have got between 0 and pi, we've got basically this positive part over here. Now the maximum value of y is 1 on the graph of sine. So what that means is on the reciprocal graph, it will be a minimum of 1 over that 1, which is just the same as 1. So what ends up happening is you have a graph that minimizes, that has a local minimum at 1 over there. And this is how it looks. It looks like a bucket almost. It's going to come down like this. And then go up. So that is the graph of cosec between 0 and pi. Now let's look at what happens between pi and 2 pi. In a similar fashion, we're going to go down to -1 over there. So y equals -1 on the original. So on the reciprocal, it's 1 over -1, which is simply -1. So again, we're going to have a local maximum over here, and it's going to come down like this. And on the right, it's going to do something similar as well. So the graph approaches the asymptote, but never touches it. And basically all you got to do is you copy and paste that section that we've just drawn to the left-hand side between -pi and 0. So it maximizes over here, and it goes down like this. Very nice. And it does this. And there we go. And that right there is the graph of y equals cosec x for x between actually, probably it's going to be a round bracket because the asymptotes are not included. So from -pi to 2 pi, that's what we've got. Let's list a couple of other properties that will be useful. Now, normally for sine and cos graphs, we talk about amplitudes. These reciprocal graphs don't really have amplitude, so we're not going to worry about that. They do have periods and ranges though. So fortunately for us, the period of a cosec graph follows the same period as a sine graph. In other words, if it's just cosec x or if it's just sine x, the period is 2 pi. If there's a number that appears in front of the x, then we're going to end up with 2 pi being divided by that number. So that's the period, and then we have the range. Now the range is a bit funny on this one because you can see the graph sort of starts down at the bottom, which is infinity, and then it goes all the way up to positive infinity. So what that means is we need to take into account both of those things with the range. Now the best way to actually write the range for a graph like this is it's all real numbers except everything between -1 and 1. So if you look at the y values between -1 and 1, let's highlight them. These y values between -1 and 1, there's nothing there. There's no y values of the cosec graph that exist over those y values. There's no actual points, and therefore we're basically excluding all of those. Now the question is, why did I basically use round brackets around the -1, 1? Well, it's because I'm excluding y values. So you see that the cosec graph does go through -1 and 1, so you do not want to exclude the y values of -1 and 1, and that's why you put round brackets around that. Sweet. So there we go. That is how you draw the graph of cosec of x. Now you see I've already got period, domain, and range. So let's just copy that over into the bottom part. So the period is going to be just 2 pi. The domain, well, the domain is all real numbers except positive integer values of pi. So I'll just put n pi, and then I'll say that n is an element of z, all integers. So basically, the domain of this function, domain of this graph, I should say, is basically all real numbers except where the asymptotes are. Now the asymptotes exist at neg pi, 0, pi, 2 pi, 3 pi, 4 pi, etc. So that's just integer multiples of pi. So that's the domain right there. And the range we've already seen, that's all real numbers except everything between -1 and 1. Awesome, so that is cosec done. Now let's have a look at sec. Right, so in a similar way as what we did before, we had the graph of sine x. So this time we have the graph of cos x. So this time the cos x, again, it's drawn over a domain. Actually, I think I used the other notation before. So the notation is from negative pi x to pi. So we're drawing the graph of cos between negative pi and 2 pi. Okay, so now let's look at what sec has to offer. Well, in a similar way to what we did with cosec, we're going to draw vertical asymptotes where the graph of cos had x-intercepts. So once x equals pi over 2. We have another one here at x equals 3 pi over 2. Okay, and then finally on the left, we have x equals negative pi on 2. So x equals negative pi on 2. Now, fortunately, cos has the same amplitude as sine, which means that the graph of sec will really just be a translation of the cosec graph, which kind of makes sense because the cos graph is really just the sine graph moved left by pi on 2. Well, that's exactly what the sec graph is compared to the cosec graph. So this time, it's going to minimize on its y-intercept. So it's going to look like this. It's going to come down, and it's going to go up like that. And there we go. That's the first part between neg pi on 2 and pi on 2. The second part is going to maximize at pi comma neg 1 and do something similar. It's going to go down this time, like that. Excellent. And now for the most left and most right parts. Well, you can see that the maximum is basically on the right-hand side there. So we're only going to draw half of what we call the bucket part there. There we go. That part's up there. And on the very left, negative pi negative 1. It's going to do something similar. It's going to come down like this. And there we go. So there we go. That is the graph of sec x over a domain of negative pi, comma, 2 pi. That's just where on the graph we're looking at. The actual domain is going to, of course, exclude the asymptotes. Right. So what is the period of this graph? Well, as you can see, the graph starts off at neg pi on 2 and ends at 3 pi on 2. That's one full cycle. So that is a spacing of 2 pi, which makes sense because the period of cos is 2 pi as well. So the period, that's just 2 pi. The domain, actually let's make that blue. Awesome. So the period is 2 pi. Now the domain, this one's a bit more trickier. As you can see, the graph basically excludes all x values that are pi over 2. So you got pi over 2, neg pi on 2, 3 pi on 2. The next one will be 5 pi on 2, etc. What you might notice is that these are all odd multiples of pi on 2. So the way you write that is like this. So we've got all real numbers. Okay, that's the domain, except, and the way we're going to do this is it's going to be 2n plus 1 pi over 2. So 2n plus 1 is what we call an odd number generator. If you think about it, what you end up seeing is that if you take any integer and you double it, it becomes even, guaranteed. Then you add 1 to an even number and you will get an odd number guaranteed. So you've just got a whole bunch of odd numbers multiplying by pi and then being divided by 2. And n is, again, an element of z, just like it was back up in the graph of Cosec. So that is the domain. And the range, well, the exact same range as the Cosec graph. It's r except neg 1 to 1. Okay, there we go. So that's just the basic properties of this particular sec graph. Right, finally moving on to the Cot graph. So over here I've got the graph of y equals tan x, again between negative pi and 2 pi. So between negative pi and 2 pi, I've got the graph of y equals tan x. Now notice that the graph of tan actually has a period of pi, unlike the periods of sine and cos, which are 2 pi each. So here we've got just a period of pi because one full cycle, it almost looks like this cubic sort of graph. It exists only over a x spacing of pi. Right, so again, here we've got the graph of y equals cot x. So yeah, we've got the graph of tan in the background to assist us. So let's see what we need to do. So there's a couple of things we need to take care of. Number one is, of course, all the asymptotes. So there's an x-intercept on tan at negative pi. So let's draw that in. X equals negative pi. Then there's an x-intercept at the origin. So that's x equals 0. Another one at pi itself. Okay, there we go. And that's x equals pi. And finally, we have this other one, which is x equals 2 pi. Alright, so there's all our asymptotes. Now, the graph of tan had asymptotes at negative pi on 2, and pi on 2, and 3 pi on 2. So what that means is asymptotes on the original tan graph now becomes x-intercepts on the Cot graph. Okay, so what is this going to look like? Well, let's look at the spacing between 0 and pi. As x approaches 0, the graph of tan approaches y equals 0. So what that means is the graph of Cot basically shoots off to infinity. And basically, as the graph of tan increases, the graph of Cot is going to decrease. So that's what you get. And then likewise, when you jump over to the right-hand side of pi on 2, you basically have the graph of tan going from negative infinity to 0, which means the graph of Cot will go from 0 to negative infinity. And there we go. That is the graph of y equals cot x between 0 and pi. And basically all you got to do is copy and paste that same graph over to the next cycle like this. There we go. And finally, between neg pi and 0, something similar happens. It does this, like that. And all the way down. Right, there we go. That is the graph of cot x. And I'm just going to label these x-intercepts. The other graphs didn't have x-intercepts. That is the cosec and sec. So this one, because it has x-intercepts, I'm just going to label them just for completeness. Pi into 0. And then we have negative pi into 0. So we have y equals cot x that's drawn from neg pi to 2 pi. I'm not including neg pi or 2 pi because there's asymptotes over there. Right, so the period, well, the period of the Cot graph, that is just pi, really. That's just pi. Okay, so that's just pi because the graph of tan also had a period of pi. The domain of this one, well, the domain, if you have a look at this, again, you see all the asymptotes are basically at x values that are just integer multiples of pi, just like it was in the graph of Cosec. So again, the domain over here is going to be all real numbers except n pi, where n is an integer. And finally, the range, well, if you look at the graph of this, it goes all the way from negative infinity to positive infinity. In other words, the range of the Cot graph is just all real numbers. There you go. So that concludes the basic graphs of sec, cosec, sec, and cot. So now these graphs, these are what we call the basic ones. We can transform them using our usual methods knowledge, which is your DRT, dilation, reflection, and translation. So basically, if you have f of x equals cosec, fx is cosec, fx is sec, or fx is cot, then you can transform that y equals fx into y equals a times f of n bracket x minus h plus k. And I'm using the same symbols and letters over there as what you would use on any other graph. In other words, parabolas, cubics, etc., etc. So a and n represent dilations or reflections from the x and y axes. So if a is negative, then you get a reflection in the x-axis. If a is positive, then you've just got a dilation. And then n does the exact same thing, except just from the y-axis. Then we have the values of h and k. So h is right and left movements, and k is up and down movements. So it's very important that when you sketch these graphs, it's always a good idea to follow a particular order. And that order is this. You want to first look for and identify what the period is, because that tells you basically how much how wide the graph is, especially compared to your domain given on the graph. Then you also need to go to asymptotes. Now, asymptotes are great because they give you a stencil. They give you like these boundaries that your graph exists between. So it makes graphing a lot easier. And finally, you always need to take account of endpoints, especially when graphs give you a domain, which most questions will do. All right, so let's see this in practice. Let's look at example 1, where we get to sketch the graph of y equals sec 2x over a domain of 0 to 2 pi inclusive. Right, so first things first, let us look at the period. Okay, so I'll keep the 1, 2, 3 from before in view, so we can refer to that throughout the working. Right, so 1, period. Well, a period is going to equal 2 pi divided by 2, which is equal to pi. Okay, so that means if our domain is 0 to 2 pi, we're going to have exactly 2 periods fit into this particular axis. Right, next thing is we have asymptotes. Okay, now for the asymptotes on a normal sec graph, the asymptotes are at basically pi on 2, 3 pi on 2, etc. So what ends up happening with sec of 2x is all those asymptotes pretty much halve. So if you remember, the asymptotes were at x equals all the odd multiples of pi, and that was divided by 2. So because we're halving the period, we need to halve the asymptotes as well. So they'll now end up at 2 and all odd multiples of pi on 4. In other words, they'll be at pi on 4, 3 pi on 4, 5 pi on 4, and 7 pi on 4. Okay, so that's really what happened. Now, just to make it a bit clearer, I'll actually draw that. I'll write that as 2n plus 1 pi over 2 divided by 2, and that's of course equal to 2n plus 1 pi all over 4. Okay, and then we'll of course must write the fact that n is an integer. Okay, so n is an integer. Okay, that's meant to be a z over there. Let's make that a bit clearer. There we go, n is an integer. Right, now finally we have endpoints. Okay, so basically we're going to have the endpoints at 0, comma. Now if you sub in x equals 0 into sec of 2x, you get sec of 0. Sec of 0 is 1 over cos of 0. Cos of 0 is 1, so 1 over 1, well, that's just 1. And the other endpoint is going to be at 2 pi, comma, plugging 2 pi in, that's sec of 4 pi. Sec of 4 pi is 1 over cos of 4 pi, and cos of 4 pi is also 1, so sec of 4 pi will also be 1. Okay, there we go. So that is our endpoint. So let's go and put all these things in. So 0, 1 is our endpoint, 2 pi, 1 is our other endpoint, and then we're going to have asymptotes at all odd multiples of pi on 4. So that's 1 pi on 4 is going to be our first asymptote, x equals pi on 4. We can have another asymptote at x equals 3 pi on 4. another one at 5 pi on 4, and finally the last one at 7 pi on 4. X equals 7 pi on 4. Now let's just quickly write the endpoint. So 2 pi comma 1, and on the left we have 0 comma 1. Excellent. So how is this going to look? Well, between 0 and pi on 4, sec is going to go up like this. Between pi and 4 and 3 pi and 4, it's going to maximize at -1 and just go downwards like this. And this part's going to do the same thing, downwards like that. Between 3 pi and 4 and 5 pi and 4, we're going to copy, paste, and reflect what happens between 0 and pi and 4. Then between 5 pi and 4 and 7 pi and 4, again, just copy and paste what happened between pi and 4 and 3 pi and 4. And finally, at the last part, it just comes down like this, and you put your arrows there. Excellent, and there we go. That is the full graph of sec2x between 0 and 2 pi. Let's move to our final example. We've now got y equals cot of 2x minus pi and 4 between 0 and pi. So the first thing I'd recommend with questions like these, when you've got these translations in there, is to actually take out the dilation as a common factor. So I'm going to write this as y equals cot, bracket, 2, bracket again, and x minus pi on 8. So what that tells us is we've really got the graph of y equals cot of 2x that has been moved to the right by pi on 8. Okay, so that's very important to realize. We've just got cot 2x moved right by pi on 8. So let's go and identify the period, asymptotes, and endpoints. So the period, well, the period of the basic cot graph is just pi. So the period of this one is going to be pi over 2. So the 2 in front of the x basically halves the period. Number 2, the asymptotes. Well, the asymptotes of cot used to be at all n pi's, so basically all the values, all the integer values of pi. So what that means is now they're going to be at all the integer values of pi divided by 2. But remember, we're moving right by pi and 8, so you simply need to add pi and 8 to it. So we have n pi on 2 plus pi on 8. That will tell us how to get the asymptotes. Finally, number 3, we have got the endpoints. So at 0, let's plug in 0. So cot of negative pi on 4, that's 1 over tan neg pi on 4, which just happens to be -1. And finally, we have the other one, which is at pi. So pi is going to be our final endpoint. We plug in pi into cot 2x minus pi on 4. You get 2 pi minus pi on 4, which is going to be 7 pi on 4. Tan of 7 pi on 4 is -1. So cot of 7 pi on 4 will also be -1. Right, so what I'm going to do is I'm going to start by putting the endpoints in. So 0, -1. And of course pi, comma, -1 as well. Okay, -1. Right, our period is pi on 2. Our asymptotes are going to be n pi on 2 plus pi on 8. So what you can do is you can simply, I forgot to write n element of z. It's very important. There we go. So I'm going to plug in 0. That's the easiest one to plug in. And we end up with pi on 8. Okay, so we're going to have one asymptote here at x equals pi on 8. Now we need to jump forward by pi over 2 because all the asymptotes are spaced pi on 2 apart. Okay, so how do you jump forward by pi on 2? Well, you just need to jump 1, 2, 3, 4, 4 ticks to the right. Why is it 4 ticks? Well, because each tick on the x-axis represents a spacing of pi on 8, and therefore 4 of those ticks gives you a pi on 2 jump. Now that right there, that's 1 pi on 8. We're jumping right by 4 pi on 8. That one is going to be 5 pi on 8. Excellent, so there we go. We have our two asymptotes. We've got our period as well, which is pi over 2, and we can see that there's two periods in there. You'll see one full period between pi and 8 and 5 pi and 8, and then you can see a split period between 0 and pi and 8, and finally between 5 pi and 8 and pi. Alright, let's just draw this quickly. Let's get it going. Here we go. Whoa. Let's try better. There, that looks pretty good. Now between pi and 8 and 5 pi and 8, we're going to have an x-intercept right here at 3 pi and 8. So it's going to start up here, come down like this, and keep going down. There we go. So that x-intercept is 3 pi on 8 comma 0. And that endpoint actually should be a bit down. Let's just fix that up. There we go. Grab that, moving it down right there. Cool. That is the endpoint there, and it's gonna do this. So x-intercept is going to be right here. It's 2 ticks to the right of the asymptote. You can use the other period, the other cycle to see that happening. And finally, it comes down like this. Here we go, like that, and ends on that endpoint. And there we go. So that one right there, that is 7 pi and 8 comma 0. And there we go. That is the graph of cot 2x minus pi on 4 with all the translations there, the endpoints, the asymptotes, x-intercepts, etc. So before we end this, let's just quickly have a look at the calculator. So I've actually drawn this on the calculator as well. So here is the graph of cot 2x, cot of 2x minus pi on 4, and basically you can see it's the same thing as what we had on here as well. So you've got this small part here, which is down there. You've got this full cycle between pi and 8 and 5 pi and 8. Then you've got this sort of 3/4 of a cycle on the end. Excellent. There you go. That is the end of the second part of 3A. Hopefully all that made sense. As always, any questions, please ask. Good luck with the exercises. You can use the graph axes that I've constructed to help you with the graphing. It will make it a lot easier. So there we go. That's all there is. Thanks for tuning in. Hope this all makes sense, and see you next time.